Right. Start. Do you guys have any particular Apple problem that you want to solve? I'm trying to pull up Blackboard right now on my computer. But do you know any of the questions that you haven't gone over yet in class? Let's see. Let's pull up the sample questions. Really any of the ones that have to do with well, yeah, that, yeah, like the actual one you have. Yeah. This one? Yeah. Yeah, this one right here. Yeah. All right. This is spring 2009. Problem 2. Okay. We have two-phase power source. Okay, in Y. Always the first thing you do is draw it out. And phase voltage is 120 and 0. That's connected to another Y load. Each of the phases have a power of 1152 and J864. So you're given the complex power factor. So we know S that times Pf. So yeah, yes, over that E is given as 52. This will be plus 864. delta. So 11. So this is P plus JQ. Add 28. This voltage is from this to neutral. That's 120 volts. Okay. So load impedance. For the load impedance, what we can do is Z equals to V square over S. This comes from S equals to V square over Z. We already know that from V squares are. So from there we have Z. And since you have three phase, and both are connected delta or Y connected, you can treat each of them separately as a two single phase analysis. So this will come out to be it's something like this. This is given 120. Yeah, that's 150, and this is given as square over S square is 120 square. S is whatever that comes out to. That is a form of the third part is asking for what capacitance you need to make the power factor 0.995 lag, and the frequency is given. What can you do for that? Let's see.
Sorry, I didn't answer the question. It was saying the new power factor should be 0.95 lag.
Yes, and we have to add a capacitor in parallel to each phase. So we have to find the capacitance. Hey. So we're doing spring 2009, and question number 2, to just briefly go over whatever we have done so far is, first question asks for what is the power factor of the load. That's the circuit we've been given. So always the first thing you do is draw out the circuit to get partial credit for that. You have phase voltage of 120 volts, and the complex power is given per phase. So to find PF, we use the formula. Real power is the magnitude of complex power times the power factor. From there, we get the power factor that way. Next, it asks for load impedance. We use this formula. S equals to V squared over Z. We switch it around, so Z equals to V squared over F. And we calculated that. I didn't get the answer, but we can try it. For the third one, it's asking for, it's given us a new power factor of 0.95 lagging, and it's asking for the capacitor we need to put in parallel with each phase to get to that new power factor. Currently the power factor is 0.8. Is it lagging or leading? What do you think? This power factor? How do you think? Well, it's a power factor is always less than or equal to 1, regardless. Yes. It's positive. Since it's positive and we know that current is the conjugate of power, right? Current would be negative, and negative is lagging. So it's lagging. So it's still lagging over here. So since you have the PF, we can find the Q from the new PF. Let's find the angle first. So theta equals theta inverse (0.95). What does that do? That's a new angle. We'll be keeping the power same, or complex power the same. So Q of the load is going to be magnitude of S times sine of 18.2. Yes, that's this part of it.
Yeah. I can't check these answers though because you didn't put the spring 2009 answers up. But you guys know it's like over in class. It's over. I think the cheat showed
Oh, the answers are less important than the way we're doing it. So always show the steps of your solution to get partial credit. You'll be checking each step along the way and find out where you went wrong and grading, depending on which parts you did right. That's the Q, and that's that. So 2O plus Q generated by the capacitor equals to E
-414.
that. And QC equals to SQC.
Isn't that?
Yes, that's in whatever that comes up to. Compare. Sure. Here. That's from S equals to V squared over Z. S equals VI conjugate, right? V times V over Z conjugate. Well, I guess, I don't know, should be. That gives you pretty good. It's equals to V times I conjugate, right? I conjugate is V conjugate, V over Z conjugate, right? V times V conjugate is the modulus of V squared. And when you take the conjugate downstairs, it's V conjugate, right? When you move the Z onto the other side and move S downward, take the conjugate of both sides, and get S conjugate over here, and S conjugate gives you another.
Well, there's 1 over omega times C, right? So C equals 1 over omega times 4/13 times 3 times 3.
Questions on this? You had a second question.
see, I don't see what it is. There, you able to use either proposal. S.
Yes, I got from that formula over there. S equals b square over L is.
Oh, I see, that's on the other.
That was given. So it's 3 times that. 3 times because there's 3 of yes. So it's given in the IJ form or rectangular form. And this is per phase. If you want total power, you'll have to multiply by 3. But it never asks for the total of anything.
Oh, so this is the complex power?
That's a complex number.
Well, why is it given in watts?
What?
It's given in watts. This is a complex power in VA.
That's probably a typo.
Okay.
But you need, the thing that it's hinting at is there's no K in particular name of it, so all your references should be in amps or ohms or volts instead of kilovolts, megavolts, anything like that.
Because,
It should be actually MP or V.
oh, right, because it is complex, so it shouldn't be power. It shouldn't be
Yeah. It can be
watts.
volts.
Real power.
Yeah, this part is the real power.
Real power coming in watts.
Yes.
That's my thought.
So if you see a J, real power cancel.
Right, but also, because it has, it's in watts.
Yeah. Any other questions or any, did I go over any part again? You get this part where we got the view, view from? Or where my I took Q, my I found Q or anything like that.
That's what the transformer stuff, or
Yeah, we did a couple of, we did some of the transformer programs on the sample papers. If there are no more questions from this one, we can move on to whichever question you'd like to see. Let's solve. This was spring. This body part, we did it. The professor went over this in class as well. So you should practice the tables from the book, or if you write it out on the cheat sheet, you can use it during the test.
which one do you guys
Yeah. Explain, 2009, I know you didn't put the yeah, I know.
No.
So we just did one from the beginning to the final report. So other than that,
That transformer.
it's not that tough, but.
This one?
Just like it, but if we look, we probably, most of the cosmetic, I would say, in my opinion, 2010, or.
Fall 2010?
That's my.
No, yeah, I'm up for it. Practice.
Which one from that?
Yeah, there's one power one and then there's
Yes. This one? Yeah. Let's do it and figure it out. Okay. It's fall 2010. So what's the first thing we do here? Yeah. Doesn't say delta or y. So, we can think of it as delta. I guess it's not that important. So we didn't get it done. We have a load. We have two loads.
Yeah, but I thought one was one, the other one was, I thought one is delta, y. Right? One is like line is one. And then delta, are we going to have to convert it?
Let's look at the problem. It's asking for finding the power factor of load 2 and whether it's leading or lagging. So y connected source and the impedance is given. So you can find the power. Another formula for power factor is E over S. You can find P and you can find S. So find S and then you can do this part. So you're right. Since second one is Y connected, you have to find the or the line neutral. That's going to be, we have 3 kV. So what's the formula for finding line to neutral from line neutral?
It's the square root of 3 times
It's the line line.
yeah,
Or yeah, look at the notice already.
Oh, you know, must be
PLN is line to neutral. We have 3-phase power source. This is neutral, whatever. So from here to here is the line to neutral. And from here to here is the line. Okay. What does this come up to be? The line line is 3 kilovolts. So the 3 actually right unit at the end. Okay. So B, you have R, find S. Over 80 plus 260. So 80 minus 260. Ohms. S?
What's that? That is root 3 times. Or you just
Root 3 and 30.
is that
And PF is going to be whatever the real part of that. We get magnitude. So that's a power factor. Also have to figure out whether it's leading or lagging. Lagging if it's positive, or the key is positive. Okay. So find that out.
we're just squaring 3,000 and putting it over that, right?
Second question is asking for total complex power of the two. We have the complex power of the first one already. The second one we have been given real power. We have the real power and we have the PF. So we can find the magnitude of complex power. Use this formula. And from here, we'll find the angle. Power factor. And we'll find reactive power. Reactive power. Then you add the two together. Are you teaching question?
Or one that's down there. You get that PQ over there, like,
Here?
Up
Or
right there, right here.
yes.
You get that mess. Is that really up to the student over there? So they check.
For power factor, you don't need to double or triple it. For total complex power, okay, we found, okay. So this is giving you the total complex power, and for P1, P2 and P2 we found only for one thing. So you have to multiply this by 2.
Leading means that's objective power, that's the angle is going to be negative.
Leading means that for powers, Q is positive, lagging.
Okay, and that's
For current,
complex power.
yes.
Brian, would you find PF if you put a P over magnitude, where it's like radical P squared plus Q squared? Is the P on top, is that the, like, is that the 3 locals, or is that P that you obtain from the complex power?
For this one, right?
Wait, no, down. Oh, right there. Yeah, this little P over the square plus Q squared. That P on top is, that's what you find up in the line above, right?
Yes.
Okay.
These are all for the second one, and this is per phase. For this one, we use the total complex power. Once you find this, the power factor is going to be again.
Scroll up.
Also, can help you with stuff. This is from Saturday. Probably no days left. Are you good with everything? Here. Let me double check. Somebody there. Which part? To where? So next question is asking line current. Okay, so for that one, line current.
Let's see, if I use that, we know the line voltage, we know the power. Telling the phase voltage. Wait. Okay.
Define, yeah, total S. Going to be P and S. So okay, what is it?
No, just, we didn't need to multiply P2 by 3 until we were adding both together. So, okay.
Yeah, because when I found P1, the power load 1, I used the total power that was given, which is for all 3 phases, total for 3 phases. But when I found for load 2, I did impedance was per phase, so I have the power per phase.
You scroll down, actually, a bit so that equation, or the power factor. Yeah, that's a bit.
Does this part make sense? You know the total power? This is I line. Neutral. So each voltage source produces a third of the total power. We have this voltage source times conjugate of IL equals to the third of the total power that we have. So we use that formula. S total equals to IS conjugate times VLN, V line neutral. So that's per phase voltage, and we change that around. I then the IL. Next, we need to find phase capacitance of a Y-connected three-phase capacitor bank. Just going to put an arrow, load, make total P equal to 1. So for P equals to 1, If equals to 1 when Q total is 0, 1 over C. V squared. Okay. So I made a mistake in the first problem. The here. What should have? So this one I found the Y connected capacitor bank. So it's going to be V squared. Over V. Right? That's the formula for finding power across power of the impedance. Okay. Still on. Impedance of the capacitor 1 over that carried over there. Now it seems. Let's do that over here. Q total equals 0. Power from the capacitor is per phase. And the total. And this is Y connected, so the voltage across the capacitor is going to be the voltage line neutral. Line neutral over C. And over C. Just keep in mind that there's voltage line neutral is in kilovolts. So you'll be squaring kilos. So that's 60. And that's going to be Q is in. Q is probably in kilobars. So that's 1,000 amperes. Okay. Next question asks for same thing, capacitor bank, but in delta. So there's a relationship between C delta and C y, right? C delta is 3 times C y, something like that. So if you put that in directly, I don't think the professor will mind. Otherwise, you just use instead of voltage line neutral, you're using voltage line, which is V line neutral times square root of 3. It's going to be 2 times that. It's going to be 1/3, I think. Can't remember. Three times out, that's 1/3. So I will check this. Next it's asking for line current. And the capacitor bank is connected parallel with the loads. At that point, you know the total complex power, because Q is 0. That's R. S is going to be Q. That's S. Just 1/3 of that, or the other. At the complex power and the power factor of the source. I don't understand the point of last question, because we already said Pf is equal to 1 right here. And we found the concept, and when Pf is 1, complex power is just equal to the real power. Q is 0. I don't see that's there. Let's check the answer. It's going to be fall 2010. Here, Cy is 3 times C delta. That's correct. Source voltage is the same as voltage source. Power equals total load power. Okay, thank you for coming. Well, it's asking for the complex power of the source, which is same as the complex power of the source. I think that's all we have to say. Because we're neglecting all losses. There's no loss in the transmission line. So you can just say that it's equal. You already found complex power here. So you can say that's the same thing as the source. Alright, that's all the time usually for the supplementary structure session, but I can stay here for 25 more minutes if you guys have any other, want to go over any other problem. Mm-hmm. Yes. Yeah, because we said the total power or reactive power produced by the capacitor is equal to the one consumed by the load. So they cancel it. That's only because the PS is, the new PS is 1. If you had something like 0.95 like the previous question, it would be different. See if you have another problem like this. Which one?
Not close that one out.
Okay. Move it to the side. Here's the similar one. And another similar one. Get this one. This one. So for ECE 213, I don't think there's ever transmission line expenses. So you don't have to worry about that. Does this have transmission? Oh man. Stand corrected. Okay. For this one, yeah, the voltage will be different. Yes. For this one, it says delta connected source, so it helps to draw out the circuit. Let's draw it out. Like that. Let's draw this out. Three-phase delta connected source. I don't remember how to process and manage it. Like that. Now, and one Y-connected three-phase load. And you have a transmission line impedance of 1 plus J2. I didn't leave any space to draw. That. This. The phase voltage is maintained at 2500. So, the frequency is given. Load is consuming 96 kilowatts. That's total, so it will be 32 per phase. Power factor is given. And the line current and overall loss of we know the phase voltage and we know the power consumed. You can actually find the total the magnitude of complex power. The entire phase, 32 over the 40. So, to KVL, there we can find Q. What? Really, this? It shouldn't be that way. That's so small. So this is sine of cosine inverse, which would be sine of 36, 27, 24. It's 24 bar. Whatever. Okay. You find Q, and now you have the complex power. Line current plus the complex power S over 294, which is given. Or the cross J24 over
This is lagging.
yeah. Okay. 2500. Okay. P plus A. These are in kilo, so 1,000 times it by 1,000. That's kilo over kilo is the amps. So once you have the line current, loss into the current to Z line and Z line is given 1 plus J2. It's asking for real power loss, so it's time for this is the real part of the answer. Yeah. This time, this you it distributes into times 1 and times 3 too, right? And the part that's only times 1, that's giving you the real power. So that's,
So you find the load current, that's what we divided S bar by S by 3.
Reading per phase, that's what you did, S by 3. And since it says doesn't say per phase, so you probably have to multiply by this by 3. This is per phase, times 3, the total loss, total is 3 times.
Because the voltages are low there. We have to make.
Next part is an interesting part that's not really done. When I saw in previous assignment sessions, we didn't see any of this. So we'll do, for the next part, since it's asking for line voltage, what we can do, we can find the phase voltage. We'll do per phase analysis. We'll do per phase analysis of the circuit. We'll find the per phase voltage of the source. From there, we'll find the line voltage of the source. We have 1 plus change. Do we find this? We know this one. Yeah, we know the current of this. So we can do a KVL as negative the source line neutral per phase plus I line that we just found, Z of line, so 1 plus V. Plus 2500. That equals to 0. Yes, line neutral. We decide to go into power engineering. We'll see a lot of this. Well, regardless of which direction we want to go to, we'll see this thing is good in ECE 319. Okay, so we find ESLN from there. So ES line to be square root of 3. Square root of 3 times neutral. This is correct, right? That's how you do the calculation, right? Or do we just do the square root of 3? Okay. You already know how to find the capacitance and what's unity power factor. Equals Q equals to 0. You can also find CUI at CUI equation. Whichever seems easier.
And we say VS because it was VS. No, yeah.
And also,
okay.
at this point, you notice since it's asking for total load power factor to be 0, Q is going to be equal to the Q of capacitance is going to be equal to Q of the load. We can, well, calculating it doesn't take into account the Q of the transmission. What was your question?
No, just making sure I'm kind of patient. Yes, source. Yes,
LL is line 9 and S is for source.
and if it doesn't, so if it doesn't have an S, I mean, it's comes to load. Like usually when you just put the line in, the line neutral, the load, the whole thing.
So it depends on what we're being asked for. I don't use the same notation every time. This one we actually have to find the source, and I think I didn't use a subscript for when I was looking at the load. That one's the load, and this one's source differently.
And the way we know when it says, I guess the key word is like phase units, but it's just that one of the three. Or it says line, that's Y.
Hey, Where?
Okay. Okay, so because it says the load is consuming 96, you said we gotta put that in there.
For per phase. Since we do per phase analysis every time, because it makes things easier. Like that.
Oh, okay.
So we did divide by 3.
Okay, so when it's a 3, we always do it per phase, and then we just turn it to total load. If they have.
If it seems easier, then we do per phase.
But there's no notation to show like that this is taken like per phase. Because I could just as well say that PV, I'm just trying to get understand. Like I said, P equals 90 times 96.
Yes. So when it says the load is consuming 96 kilowatts, you know this is a 3-phase load. So each phase will consume 1/3 of the next load. But we saw in a previous program that it was given as 3 times a certain amount. So you know that the amount of clearances that the amount per phase. When you're given just voltage and it doesn't say anything, it's usually line 9 voltage, and it's usually the RMS voltage, or by default, if it doesn't specify anything. Oh, there's nothing else up there.
No, down. Okay. That should be on. Oh, this should be 40. Should that be on?
Here? All right. I think so. Yeah, that should be 32. Yes. That's P from over here. So this is probably not correct. This is probably something else. Hold on, only the 16 part is wrong. Okay. This is also a similar problem. You can do it a similar way. This looks similar to the one we did solved first. So you have a one Y connected source, one Y connected load, and a load that does not specify if it's Y connected or delta connected. No, I don't. Since you've been given the real power, or you've been given the complex power over here, you can actually find out the voltage or current from here, or impedance. There will be enough information. Then once you find voltage or current, you can probably do per phase analysis from there. That's all the time I have. I'll save this. S loss. For tomorrow's one, make sure you write down all the formulas, practice a little bit of body plots. If you can't remember the sketches, draw them out on the cheat sheet. What else? Just be careful about the units, where there are Ks and stuff. So it's kilo or mega, remember those. Remember the dot notations for transformers, or remember which ratio to multiply by. Yes, coupling is on the syllabus for this midterm. For coupling, you're going to have to remember the dot notations. It helps to draw the voltage source, a dependent voltage source. What? Yeah, I'm just about to close it. For transformers, there's still the dot notation is still important, because when you have dots on opposite sides, you'll have to change the sign of the source when you're moving them from left to right or left to left. And for current sources and voltage sources, you multiply by just N. When you have impedances, you have N squared. That's to keep in mind. Well, that's pretty much it. Good luck. And hopefully if your exam turns out to be easy tomorrow, my exam will